All right. Hello, everybody. So last time we finished our approximation algorithms unit, and today we're going to be, and this week we're going to be working on a new topic. It's called computational geometry. And this is the start of the part of the class where I kind of spend just a week or so on each topic to introduce you to a breadth of different things, which span a number of different sort of models of computation almost. So computational geometry, I mean, we've already been looking at some geometric problems, right? We did linear programming, which is fundamentally geometric. But classical computational geometry really takes a focus on problems in low dimension. Problems of points and lines and things like that. All right, and it thinks about things like, you know, intersections and containment of geometric objects and so on and so forth. We'll be seeing a bunch of different examples of this. Underneath all of the geometry, there is math that has to be done on the coordinates, but we tend not to worry about that. We're just going to talk about, you know, computing the intersection of two lines, and we want, or computing the length of a particular line segment. And we're not going to worry so much about the fact that, well, sometimes these numbers might be irrational, and you have to worry about precision and round-off error and so forth in your computations. That we're going to set aside and just focus on the geometric objects. And what really differentiates computational geometry is the way it thinks about taking advantage of this low dimensionality. The fact that we're looking at 2 dimensions, 3 dimensions, sometimes 4 dimensions, means that, for example, you can afford to be exponential in the dimension as you design your algorithms. You can afford to spend a lot per dimension as long as you're not doing a lot per point or line in the input to the problem. And so we're going to see several techniques that work using a kind of recursion on dimension. So in order to solve a d-dimensional problem, you use some kind of recursion to transform it into a d-1 dimensional problem. And that recursive step might be quite expensive, but because you start with a very small d, you don't accumulate a lot of cost through that repeated reduction in dimension. And so this is a technique that really doesn't have an analog when you're looking at graph problems in traditional combinatorial optimization. And in fact, we already saw an example of this kind of dimension reduction way back at the beginning of this class in the first week. Does anybody remember what we did there? Yeah?
We did like the persistent data structures to solve like the polygon point.
Exactly. We looked at this point location problem, right? Which polygonal region contains a point. And if you think about it, we did that. We talked about how we're going to think of, you know, we have this XY coordinate system, but we're going to think about X as time, and we're kind of moving a one-dimensional line through time, right? And so we were taking this 2-dimensional problem of locating a point and turning it into a 1-dimensional problem that we solved at many different times, right? So that's an example of this kind of dimension reduction. And this week, we're going to see some more examples of that. So the first example, the first problem that we're going to be looking at is kind of a dual to that point location problem, known as orthogonal range searching. Okay, so with point location, we had a collection of lines that we wanted to query with a point. In orthogonal range searching, we're going to have a collection of points that we want to query with a region. We have a set of endpoints that we want to pre-process so that we can then take a query rectangle and then we want to output the points in the region. Okay. And there could be different forms of output. We might just want to do an emptiness test. We might want to count the number of points in the region, or we might want to enumerate all of the points in the region. Okay. Now this is called orthogonal range search because the query range is a rectangle, right? You could imagine a more general data structure where, for example, you pass in a polygon and it tells you which points are inside of the polygon. But we're going to focus on this restricted case. Okay. So I take it everybody understands the problem? No questions about the definition? All right. So when you're looking at a problem like this, and when you're thinking about computational geometry, a really nice place to start to get some insight and kind of think about what you might hope to achieve is to think about the one-dimensional version of the problem, right? This is a two-dimensional problem. What's the 1D version? Yeah?
Finding points in the interval.
Right. So the 1D version, actually I should have made this clear. I mean, we're actually going to solve it for general D, but for discussing on the blackboard, I'm going to focus on the 2D case for obvious reasons. So the 1D version is going to have points on a line. And your query is going to be an interval. So how do we solve this problem? What sort of data structure might we use to be able to quickly answer questions about emptiness or counts or enumerate the points? Yeah? Yeah. Binary search tree. Right? If you have a binary search tree, this lets you do count existence and counting in order log n time, right? You just search for the two ends of the interval and see if there's anything in between. Enumeration, well, you start the same way, but you're also going to have to actually take the time to spit out the points. So however many points there are, you're going to need that much additional time, right? And obviously, you can't do better if you're going to actually write down the points. Okay? So this is what we achieve in one dimension, and this kind of gives us a target, right? This is an easy problem in 1D. It doesn't take us very long. And so we can hope that it will also be a relatively easy problem in higher dimension. Okay. Oh, I should also ask, because this is an equally important question, how much space does it take to maintain this data structure? Yeah?
Linear.
Yeah. So this is order n space. Okay. Let's go to the 2D version. So again, in computational geometry, the way you often think about higher dimensional problems is by sort of breaking them down into lower dimensional problems. So we might hope, for example, to solve each dimension separately. Okay. So what you could imagine is I can take my collection of points, right? I have my x and y axes. I can say, oh, you are querying some rectangle, and I want to report the points in the rectangle. All right, why don't I think of the rectangle as having a projection onto the two axes, right? And so now this rectangle defines an interval over here, an interval over here, and so I know how to query intervals, right? I can find all of the points that are in this x interval. I can find all the points that are in this y interval, and now I just need to intersect them in order to get all the points in the rectangle, right? So how's that going to do as a solution? Yes? Huh?
O-event solution.
O-event solution. How come?
Many of the points that are not part of the solution might be included as much as O-event.
That's right. So we have a problem here that it is possible that there could be tons of points that are in one of the intervals but not in both. Okay. And so separately finding points in the two intervals and intersecting, right, it could end up costing us order n, even if the number of points that we want to enumerate is very small, right? We know that there is a cost to enumerating points, but we're going to be paying much more than that if the number of points that we enumerate is small. And in fact, remember that in the 1D problem, we were able to count the number of points in log n time, no matter how many of them there were. Whereas here, in order to do the counting, we would have to actually enumerate the points and count them. And so this would add this linear cost even to the counting problem or to the problem of just determining existence. So this doesn't work very well, right, to just intersect these two intervals in a naive fashion. Okay? So how might we hope to do a little better? Right? So too many points in the separate dimensions. So that doesn't work very well. How might we do better? Well, let's go. I mean, this may start off sounding a little bit crazy, but you know, if I know that this is the x interval, that's interesting, right? Then I know all the points in this x interval, right? So I could just focus on the y interval searching for points in this x interval, right? I could just put I could take all the points in this x interval and put them into a y searching data structure, right? Now, I claim that would give me a very fast solution to the problem, right? If for every possible interval I had a search tree on the y coordinates of points in that interval, how long would it take me to solve these three range query problems? Yeah?
Log in.
Log n, right? So, idea. Let's put a y search structure on each x interval, right? Now we have to flesh this out a little bit, right? There's uncountably many x intervals. We can't really put a y search on every single one of them, right? But how many of those intervals actually are meaningfully different? Yeah?
And choose 2.
And choose 2, right? So really, we only need to differentiate by their leftmost and rightmost data point. right? So there are only n choose 2, or at most n squared, distinct intervals. So really, we only need n squared of these Y search structures, right? We can, given the query interval, we can take the x query interval and use a binary search tree to find the left and rightmost points, which identifies the interval. And then we can search the Y structure that corresponds to that interval. And so we're doing a couple of binary searches we're using the one-dimensional binary search tree to identify the interval. We do two searches in the binary search tree. And then once we've identified the data structure, we use a couple of binary searches in the corresponding Y structure to actually test emptiness or count or enumerate the points, right? And so the time for this is basically 4 of the binary searches plus k if you're enumerating. Right? Everybody happy with this approach? Makes sense? Okay, so what's the downside of this approach? Yeah? Yes. So the problem is space plus construction time. Right? So if we think about the space, we are making n squared binary search trees. Right? Which is going to take us n cubed space. And on top of that, we have to build them. So it's going to take us n cubed log n time to actually build these n squared different binary search trees. So it's fine in terms of query performance, but the data structure itself is really unsatisfactory. So how might we do better? Yeah?
You can build a binary search tree on the x-axis. That's built on the binary search tree on the y-axis. That's the universal binary search tree.
Sorry, we can build a binary search tree on the x-axis that what?
That's built on the y-axis. So we have two-dimensional binary search tree.
What is the meaning of a two-dimensional binary search tree?
So basically, every node represents a range of x values.
Uh-huh.
And in that range, that represents the y.
Good, good. So yeah, so what we're going to do is, instead of having two completely separate dimensions, we're going to kind of interleave these dimensions somewhat in order to reduce the cost of redundancy, right? Many of these binary search trees actually are going to have almost the same points in them. So it's silly to have entirely different binary search trees for all of the different n squared intervals. You could actually sort of take the persistent data structures approach, right? And think about adding points dynamically and maintaining the intermediate. But this will only save you 1 factor of n. We're going to do better than that and save you 2 factors of n. Okay? So let's refine this idea, as was just suggested. Let's start by building a binary search tree on the x coordinates. Right? As was discussed above, as was discussed before. Let me try and make this pictorial. I don't know if this is actually going to work, but let's try. Put the points down here. I can build myself a binary search tree that represents the x-coordinates of the different points down here, right? So, this binary search tree is going to represent the points in this interval, and so we have this sort of correspondence between intervals and this binary search tree, right? And what's important here is that each internal node of this binary search tree corresponds to an x interval, right? Spanning some of the points. Okay. So, and in fact, any query interval corresponds to just order log n of these subtree intervals. Okay. To see this, right, imagine that I'm going from this point over here to, say, this point. Well, let me make it, yeah, to this point over here. Okay. Again, we don't need to worry about numerical differences, right? If two intervals contain the same set of points, then they're combinatorially equivalent. But now, if I'm interested in the points between here and here, essentially I can take this single node subtree, right? And I can also take this pair of 3-node subtrees, right? And together, these 3 subtrees will cover the entire query interval, right? More generally, right, the left path, the path to the left endpoint and the path to the right endpoint will sort of trace out different subtrees that are needed in order to make up the entire interval, right? Every time you go, every time sorry, is that pictorially clear, or do I need to sort of expand on that? Make sense? Okay. So we can assemble any actual interval that's going to be queried from just order log n subtrees, right? We're going to use, in fact, at most 2 subtrees per level. One as we go down the left side and one as we go down the right side. Okay. So what we do is, for the points in each internal node's interval, we build a Y-search data structure. Okay. And since the whole interval that we're querying is the union of these subtree intervals, right, we can count or test emptiness or enumerate all of the points in the entire interval by taking the union over all of these subtree intervals, right? So we answer the entire question by querying all of the internal nodes the roots of those different subtrees. Does that make sense? So what does this do for our runtimes and spaces? What is the runtime now for testing emptiness or counting points? Yeah?
I think it's like log squared.
How come?
Because we have to do log n different lookups in the Y search trees, which are going to take log n time each.
Exactly. I mean, we have to start by identifying the appropriate Y search trees, so that's one binary search, again, on each side, right? But that's dominated by the work that we have to do to query all of those log n binary search trees in the internal nodes, right? So we do order log n Y tree queries for a cost of order log squared n time. And then, of course, plus k if you're enumerating your k points. Yes? All right. But now, what can we say about the space that this takes? So the space is determined by the size of all of the Y structures, right? So what is that total size? Yeah?
O of n log n.
Order n log n. How come?
Because the first row was size n, and the second row was two trees of size n, and the trees that also n.
Right. So again, if we made the X search tree perfectly balanced, right, then we would have one Y search tree of size n for the whole tree, right, plus 2 of size n over 2, plus 4 of size n over 4, and so on, right, which is n plus, which gives us order n log n, right? Now, even if the search tree is not perfectly balanced in this way, you're still going to get, if it's a balanced search tree, you're still going to get this asymptotically. Another easy argument for this is to notice that each data point, is in one Y tree per level, right? And therefore, the total size is just n times the number of levels, which is n log n if your search tree is balanced. Yes? All right. And the construction time is similarly nice, right? In fact, right, you can, you're going to have, you know, one subtree that takes you n log n time to construct, two subtrees that take you n over 2 log n time to construct, and so on. So this is going to be about n log squared n, right? So that's pretty good. Now, in fact, nothing that I said here is limited to the two-dimensional range searching problem, right? You can apply this recursively to get a d-dimensional search structure, right? What is the general performance of the d-dimensional version? Well, log to the d of n query time, n log to the d minus 1 n space, space, and n log to the d of n construction time. So as long as d is small, you're talking about n times polylog, which is a great runtime, right? However, this is exponential in d, so you do not want to use this, right? It's not something that'll be useful in a general linear programming setting because d can be n, right? Or even larger. I'll mention that there's a technique called fractional cascading. Which lets you shave one factor of 1 log n off and improve the query time to log to the d minus 1n query time, as long as d is bigger than 1. Okay, this does not give you constant time querying for one dimension. That would violate lower bounds. But you can actually do 2 dimensions in log n time. Fractional cascading kind of folds together. It sort of says that if you're going to be doing this sort of search, it's kind of like the persistent data structures, where we reused pieces of older versions of the data structure so that we didn't have to search them all over again. Didn't have to waste space making copies of them over and over again. So with fractional cascading, as you're searching through one dimension, it sort of conserves that progress for the other dimensions. But that's a detail. Okay. So does this completely tell the story? Well, this is great for the static version of the problem, right? You get the points, you build the data structure, and then you do the queries. Now, if you think of our 1D version of the problem, that actually solves the dynamic version, right? A binary search tree, you can insert and remove points and continue to make queries as you're doing the insertions and the removals. What happens if you try and do insertions and removals in the 2D version of the problem? What do you have to do in order to update the data structure? Yes.
You have to merge or review like white space.
Yeah. So we know that when you're doing a balanced search tree, right, it involves rotating nodes to preserve balance, right? And I mean, the Y search trees are just regular search trees. We know how to quickly rotate them and so on and so forth. But what happens when you insert a point and you have to balance the X search tree? Well, when you rotate the X search tree, all the internal nodes have changed. And so that means that you have to rebuild the Y search trees for all of the nodes that are involved in the X rotation. Right? And so, this is pretty amazing. This is a case where splay trees are bad. Right? Never seen that before, but splay trees go crazy on the rotations. Right? And so they're going to force you to be rebuilding the data structures all the time. What you want is a data structure that is very conservative about its rotations. Okay? And there are a number of data structures that are quite nice about this. So actually, if I remember correctly, red-black trees only ever do one rotation. Right? They change a lot of red-black bits, but they only rotate one node. And so that means that if you use a red-black tree, you're only going to be rebuilding one data structure. Okay. Unfortunately, it might be the root data structure, so it might cost you n work to just insert one more point into the data structure, so that's not good. Fortunately, there's a kind of amazing data structure called a treep, which keeps the number of rotations small and also usually rotates small trees, so that on average, the amount of rebuilding work is kept small. You might see those if you take my randomized algorithms class, which I might be offering in 2 years. Things are still a bit up in the air about exactly when that happens, but you should keep it in mind. Yes?
Would a scapegoat tree also work?
So a scapegoat tree is, so the advantage of the scapegoat tree is that instead of doing a whole bunch of rotations along the way, it waits until things get really bad, and then it just sort of rebuilds the whole data structure. And I think that would work well in this context, but I haven't actually seen it analyzed or done the analysis myself. Okay. All right. Let's see, was there anything else I wanted to say about this? No, that's it for this orthogonal range search. So any questions before I move on to the next example? Yes?
Can't we do the same binary search tree, but on like the range of values, and we get log square of max value?
Sorry, we're already getting log squared.
No, this is log square of n, but we can make log square of max value.
Oh, you mean if you were assuming integer coordinates or something like that? Yes. If you have integer coordinates, there are other tricks you can play, just like in the one-dimensional case, right? So, we know that if you're sorting integers, you can do things like counting sort and radix sort and so forth. And similarly, you can use radix tricks in order to improve the performance of range search. Okay. I don't have all of the runtimes in my head, though, but definitely there are classes of data structures that take advantage of integrality in higher dimensions. Okay. Other questions? Yes?
What is like the best result for the dynamic case?
So for the dynamic case, let me think. In the 2D case, using treeps, you can improve the amortized update time to log squared n. Okay, because again, on average, it changes a very small tree. All right. I'm not sure what you get with scapegoat trees. Okay. But the general story is that the update time is polylogarithmic as long as d is a constant. Okay. All right. Changing gears, I want to introduce you to another famous problem in computational geometry, known as the convex hull problem. So again, the input is a set of endpoints. And what you want to output is the convex hull. What is the convex hull? Well, it's a polytope. It's the smallest polytope. Whose vertices, or actually, let me be more general than that. It's the smallest polytope containing the input. And it turns out, this is pretty obvious, that in fact, the input points will be the vertices of the polytope. Okay. Now, in the 2D version, this polytope is just a polygon. And the output that people usually like is the list of vertices on the hull in, say, clockwise order. Okay? This is a very nice representation because now you can just walk around the convex hull, which is useful for various applications. Okay? So notionally what you're doing is you're taking your collection of points and you're snapping a rubber band around those points in order to get the convex hull. And so you'll notice that some of the points are inside of the convex hull and others are vertices of the convex hull. Okay. Now, you can have a sort of special case where there is a point that is on an edge of the convex hull. But this can only happen if you have 3 collinear points, right? And that is kind of the special case that can make you divide by 0 in the wrong place. And so to keep things simple, we are going to assume general position, which just means that there are no 3 collinear points. This doesn't actually matter much for the algorithm I'm going to be telling you about, but it's a common assumption in computational geometry to just avoid pathological situations. And you can always get into general position by just assigning an arbitrarily small perturbation to each of the points so that they fall off of whatever line they're on. Okay? Convex hull for computational geometry is kind of the equivalent to sorting in traditional algorithms. There are 17 different convex hull algorithms, each of which is used to demonstrate a different algorithmic concept that can be used to solve the problem, and they all end up with the same running times. Okay. So I'm going to show you one particular convex hull algorithm in order to introduce one of these critical computational geometry ideas, and that's the notion of a sweep line algorithm. And this, again, is about solving the problem by sort of reducing the dimensionality. Okay? What we do is we sweep a, for example, vertical line across the problem or across the input. And then we build the solution, or the part of the solution that is at or near the sweep line. Okay? And so again, we've already seen this. The persistent data structure technique that we used before was conceptually a sweep line algorithm. We swept a line over time in order to build that data structure. Okay? And we are going to use the same technique to solve the convex hull problem. We're not going to use a persistent data structure here. We're just literally going to sweep a line across and use that to output the convex hull as we go. Okay? And I'm going to focus on building the upper hull, the part you see from above. Okay? And of course, the entire convex hull is the combination of the upper hull and the lower hull. So you're just going to run this algorithm twice in order to get the entire convex hull. So let's think about this upper hull algorithm. So we're going to start sweeping, and we're going to bump into a point. Okay. Is that point on the convex hull? You say yes. How come?
Because it was the maximum point. So like if that is not if that's somehow in the interior, then there would have had to have been a higher point.
Well, so remember, we're sweeping the line horizontally, so I will just translate what you're saying and say this is the leftmost point, right? And if you think about it, that makes it an extreme point in our notion of, in our linear programming vocabulary, which also makes it a vertex of the polytope. Okay? So this is pretty obviously on the convex hull. Okay? Now we keep sweeping, and we bump into another point. Is it on the convex hull? Well, it looks like it. Okay. At least for now, it's on the convex hull. Okay. And now we keep sweeping, and we run into another point. Okay. Is it on the convex hull? Well, looks like it. Okay. So you can see that as we go, we're slowly building up this convex hull as we run into points. But it also looks like everything is on the convex hull so far. But suppose that we now run into this point. Is it on the convex hull? Well, yes. In fact, like every point that we run into is going to be on the convex hull at the moment we run into it. But what have we just discovered by running into this point? Yes? Yeah, that tells us that this point actually isn't on the convex hull. Right? So we need to revise our understanding of the convex hull to rule out that previous point. Okay. And now we proceed, right? We may find a few more points. It might look like we're building, we're heading towards the end of the convex hull. But maybe at some point, right, we run into another point that actually forces us to rule out a bunch of the earlier points. In fact, it even rules out this point, right? And in fact, we may be so unlucky, or sorry, I won't say unlucky, but we may run into a point that takes us all the way back to the beginning and rules out everything that came before. Right? But that's the sweep line algorithm, right? Move the sweep line right. Each point encountered is tentatively on the convex hull, but might disqualify previous points. Yes? So we need to think about how to implement this disqualification process. So, looking at this visually, how do we know what points get disqualified when we add a vertex to the sweep line? Yes?
You have to always turn right.
Exactly, right? The notion of convexity, right, the definition of convex hull sort of says that as you move along the convex hull, you're always going to have to be taking right turns, right, if you look at it from this side. Yes? And so if we add a point that creates a left turn with a previous point, then that point gets disqualified. And if you think about it, the sort of most egregious left turn is going to be from the point that we just added. Right? And so we can start by ruling out that point. And then we can back up and see if there's still a left turn at the previous point. And if there is, we can back up further and see if there's still, right? And we just can keep on disqualifying points until we get rid of all of the left turns and get back to a place where there was a right turn. Okay? So the way we disqualify by moving backwards. Eliminating points that cause left turns. Right? And each point that is eliminated, we have proof that it's not part of the convex hull and should be ignored. Right? On the other hand, any point that does not get eliminated, right, there's no proof that it's not on the convex hull because, in fact, it is on the convex hull. So what's the time taken for all of this? Yeah?
Should it be linear because each point gets added once and eliminated at most once?
Exactly. So the time taken here is order 1 per point added, which gives us order n, right? And then order 1 per point deleted, right? But each point is only deleted once. Or at most once. So this is also order n, right? And again, as is usual with computational geometry, I'm sweeping under the rug the exact math of how do you compute whether it's a left turn or a right turn, right? That's some basic algebra that you perform on the coordinates of the points, okay? And there might be precision issues, but we're not going to worry about them, okay? So is this an order n time algorithm for convex hull? Yeah, in the back.
We have to sort the points.
Exactly. So after sorting by x coordinate, right? So we need to do that x coordinate sort in order to be able to visit the points in order. And we have to be able to visit the points in x order in order to implement this algorithm. So this is an order log n time algorithm, or sorry, n log n time algorithm for convex hull. And it turns out that that's the best you can do in general, right? And I mean, it's great. But there's in fact, you can give a reduction between convex hull and sorting. And they actually go in both directions. If you have a convex hull algorithm, you can use it to sort. If you have a sorting algorithm, as we see here, you can use it to compute convex hull. So the runtimes are identical. There is something slightly better that you can do with convex hull. You can actually achieve order n log k if there are k points on the hull. So if you have n points, but the convex hull is a triangle, then you can actually solve it in linear time. Okay? And so this is a place where convex hull is slightly different from sorting. In sorting, obviously, you want to output all of the points. But for convex hull, you only care about the points on the hull. And so there's some techniques for sort of rapidly getting rid of the points that are inside so that they don't use up a lot of your computational time and let you focus on the points that are on the outside. Okay? But that's pretty much the end of the story for convex hull, and gives sorry, this is by Chan in '96. So that's the end of the story for convex hull. And I think that that marks a nice place to take our 2-minute break. Okay. Sorry, any final questions before we move on? All right, 2 minutes.
Oh yeah, that sounds good. I don't know.
Quad trees and off trees and stuff as part of what you covered there?
No, all I did was this particular example of sort of an augmented one-dimensional search tree. We're not doing any of the other interest data structures.
Yeah, that's something I'm familiar with.
Okay.
So
Yeah.
I was just curious if it was something that you had also covered.
Nope, just this. We're only spending a couple of days on geometry before I move on to online algorithms. So I have to squeeze everything in.
Yeah.
Are we all set on graders for this week? I mean, we don't know yet, but do we? Yeah. We're-
Or 10, yeah, we're good.
Okay, good. Good, good, good. All right, let's pick up again. I want to quickly mention, we're going to be moving on to a really cool problem in data structure, but I want to quickly mention two kind of straightforward applications of this sweep line idea. The first is to something called half-space intersections, which lets me tie some of what we're doing back to linear programming. So think about the problem of linear programming in 2D. Okay, so you only have two variables. Okay, but you could still have a number of constraints, right? So if we think about the two-dimensional version of linear programming, right, each constraint is a half space. Okay, and so the polytope that defines the constraints is an intersection of these half spaces. Right? I'll just draw the directions of the constraints to make clear that there is an interior to this polytope, right? And if you think about it, in 2 dimensions at least, there's a nice representation of the polytope, right, as a sequence of edges and vertices in clockwise order. And if you have that representation, then it becomes very easy to solve linear programs, right? If somebody gives you a direction, you just need to figure out where along that polytope is the optimum direction. That's a lot easier than running the simplex algorithm. So if you can take the constraints, take the half spaces, and construct this half space intersection, that becomes a quick solver for these 2-dimensional linear programs. It also has other applications to just test whether the intersection of a collection of half spaces is empty or not. Okay? So there's a nice way to solve this because there's a duality between points and lines. Essentially what you do is you map the point AB into the line of points xy such that ax plus by plus 1 is equal to 0. Okay? And what this is essentially doing, and I'll do this right here in the polytope, is that the line corresponds to a point that is, this is the origin over here. Let me draw it as a little O. The line corresponds to the point that you get by drawing a perpendicular through the origin, whose distance is 1 over the distance of the line. So you go through the origin and out the other side by a reciprocal distance. Okay. Now what's interesting about this duality is that if you have a point xy inside of the line defined by QR, by the point QR, that means that qx plus ry plus 1 equals 0, which means that the point corresponding to QR is on the line corresponding to xy. Okay. And in particular, that means that the point QR is inside all of the lines how do I want to say this? All the lines such that xy is in QR's line. If you intersect all of those, you get the point QR. So essentially, a point, which is an intersection of lines, corresponds in the dual to the line, which is the union of all of the dual points, and vice versa. And if you work through the details of this, the intersection of the half spaces becomes dual to the convex hull of the space's dual points. Okay? And this isn't hard, but it would take some time for me to go through the details, so I'm not going to. I'm just going to assert that our convex hull algorithm, which runs in log n time, can also solve this half-space intersection problem, which gives us two-dimensional linear programming in n log n time, which is, of course, much better than you would get from simplex. Now, the second, sorry, any questions about that? No? OK. So the second one that I wanted to do in a really quick way is known as the segment intersection problem. You're given n line segments, again in 2D, and you want to output all the intersection points. Between these two line segments. Okay. Now, the naive way to do this, which you would have tried before taking this class, would be to take every pair of line segments and compute if they have an intersection, right? Which is going to take n squared time. But with all of the deep algorithmic wisdom you've now acquired, how would you solve this instead? I claim that we actually already have developed the algorithm for solving this problem. We did so in the first week of class. Okay, if you think back to how we did that point location data structure, what did we do? We swept a line across the x-axis, right? And every once in a while, we would see a new line segment and add that to the binary search tree of the line, right? Every once in a while, we would get to the end of a segment and take it out of the binary search tree of the line, right? Every once in a while, two segments would cross, and we would swap their order in the binary search tree, representing the place where our sweep line intersects the line segments, right? And we use this with a persistent data structure to do queries later. But if we just do that directly, forget about the whole persistent data structure thing, just maintain that search tree, and as we sweep that line across the segments, it's going to encounter all of those segment crossing events, right? So the persistent data structure technique, or the technique we used in the persistent data structure, solves this problem in order n plus k log n time for k intersections. Right? The n log n comes from the fact that you have to insert and delete the n segments as the sweep line is running across. And the k log n comes from those crossing events. Right? So all of the details about this are in the persistent data structures lecture, so I'm not going to give any more details. Right? But the point is that this is now responsive to the number of intersections. Right? If you're going to enumerate the intersections, you're going to have to spend k, and this spends only k log n. Now, in the worst case, there are n squared intersections, and this will take n squared log n time. But in the in cases where the number of intersections is small, this significantly dominates the n squared time of the naive algorithm. Any questions? OK. So with those two other applications of sweep line out of the way, I want to introduce you to the thing that will be occupying us for today and also for Wednesday. And this is a really remarkable data structure, or geometric structure, which we use as a data structure, called the Voronoi diagram. Oh, sorry, I realized I should give you one other pointer. We only talked about 2D convex hull over here, right? The general solution to convex hull has a running time of n to the floor of d over 2. Don't ask me why. Geometry is just weird. Okay? And that's for d larger than 2. So you can do 3D convex hulls in n squared time, but after that, it starts to get slower. And the algorithms are significantly more complicated than 2D ones because there's no longer a notion of being able to go clockwise around the polytope. Okay. All right, so back to Voronoi diagrams. What is the Voronoi diagram problem? Well, Voronoi diagrams are used for near neighbor searching. Okay. And we are going to concentrate again on the 2D problem, although Voronoi diagrams exist in all dimensions and are equally interesting, but they're much harder to draw. So the idea here is that you've got a collection of n points, but we're going to call them sites because there are other points that come up, and we want to specifically distinguish the starting n sites. So again, these n sites, I mean, traditionally people talk about post offices. You could also talk about, boba stores or anything else that MIT students want to get to quickly, right? And what you want to do is prepare for a query point. And what you want to do is know what is the closest site. Okay? And ultimately, we are going to want to design a data structure for quickly answering this question. Okay? With all the usual caveats, right? We want a data structure that we can build quickly, that doesn't take a lot of space, and that is able to answer these sorts of near neighbor queries very quickly. Okay? But for today, we're not going to talk about the data structure or the algorithms. We're just going to talk about the geometry of this near neighbor problem. And then we'll come back on Wednesday in order to turn it algorithmic. Okay? So let's start talking about, let me add a little bit of notation. So the sites, sorry, I'm using a P, but let's say sites of S, the sites are a collection of S. And now let's talk about the structure, the Voronoi diagram. V of S. And if we think about this Voronoi diagram, right, we've got a collection of points spread out in various places. Basically, there's going to be a region near each point that is owned by that point. It's closer, that site. It's closer than any of the other sites, right? So we're going to use V of pi to denote the region that is owned by site pi in this collection. Okay? And so let's start trying to understand what these regions are. Okay? So let's take this one site at a time. So if I only have one site, what is the Voronoi region for the site? Well, it's the entire plane because it's the only option. So it's the closest one to everything. But suppose that I have two sites. What defines the Voronoi regions? Yeah?
The line that's equidistant between those two points?
Yes, otherwise known as the bisector, right? So if you draw a line between the two sites, then the perpendicular bisector between these 2 points is what determines the 2 Voronoi regions for these 2 points, right? And in fact, if we think about a large number of points, right, every pair of points is going to be competing along one of these perpendicular bisectors, right? And so the Voronoi region for a given point is going to be all the points that are on its side of all the perpendicular bisectors, right? Now, each of those being on your side of the perpendicular bisector, that's a half space, right? And so the Voronoi region for each point is going to be an intersection of half spaces. And it's therefore going to be a polytope and a convex one. Yes? All right, so let's imagine that we add a third point. Okay, why don't I put it over here? Let's see, I don't want to write echo, I don't think. Okay, what happens here? Well, I can think about the contest between these 2 points, which causes me to define another perpendicular bisector. Let's get rid of this because it's not actually here. Okay, so I get another perpendicular bisector that represents the competition between these 2 points, right? Now, I also get a perpendicular bisector that represents the competition between these 2 points. Okay, so let's draw that perpendicular bisector. Oh, what a weird coincidence. All 3 of the perpendicular bisectors seem to be intersecting at the same place. Is that a weird coincidence? I claim it's not. There's actually one year where I got into quite a bit of trouble at this moment because I actually drew the 3 bisectors as not intersecting in the same place, which made things very strange. Why are these 3 bisectors all intersecting at the same place? Yes?
Like the circumcenter.
This is, in fact, the circumcenter of the 3 points, right? Being on a perpendicular bisector means you're equidistant from the 2 competing points, the 2 competing sites, right? So this is just the point that is equidistant from all 3 of the competing sites, right? So it's, in fact, at the center of the circle through these 3 sites. Yes? All right, now, I've drawn these 3 perpendicular bisectors, and that has actually divided space into 6 regions. But there are only 3 sites, so what's going on? Yeah.
I mean, sort of there's like 6 orderings of who's closest to you.
Exactly. So the 6 regions actually define more than the closest site. They specify the order of your distance from the 3 different points. But we don't care about that. We only care about the closest site. So in particular, right, if I look over here, right, This bisector is talking about the distance between these 2 points, right? So this is actually important, right? These 3 points, these 2 points are fighting over this region. But these 2 points are not actually fighting over this region because this point is closer than both of them, right? So this side of that perpendicular bisector is sort of irrelevant for the Voronoi diagram, okay? Similarly, for this point and this point, right, this bisection matters, but this one does not. Right? And finally, for similar reasons, this doesn't matter. So the 3 bisectors actually, where they run into each other, they stop forming the Voronoi diagram. Okay? And so here we have the true Voronoi diagram for these 3 points. Okay? Now, at the moment, the 3 Voronoi regions are infinite, right? They're unbounded. But suppose that I now add a point, say, over here. Okay? Now things start to get more complicated, right? I again draw my bisectors. Whoops. Sorry, now is where my tremendous drawing skills really start to kill me. Okay, so once we add a 4th point, we start closing off regions of space and a 5th point and so on. And eventually, when one point gets surrounded by other points, its Voronoi region becomes bounded, right? So I can keep doing this. I can keep drawing these different Voronoi regions, and I get myself this beautiful Voronoi diagram, okay, which maps out these different regions. Okay. So that's an example of a Voronoi diagram. You basically get one Voronoi region around each of the sites. That region is a convex polygon, right? And once we have drawn this Voronoi diagram, we're well along towards solving the nearest neighbor problem, right? Because once we have this Voronoi diagram, what do we need to do when we have a query point in order to identify the closest site? Yeah?
Just find which part is it then.
Exactly, right? Once we have the Voronoi diagram, solving the nearest neighbor problem is reduced to finding which Voronoi region contains the query point. Do we know how to solve that problem? Right? I've got a bunch of line segments that are dividing up space, and I now have a query about which polygon contains my query point. How do I solve that? Yeah?
Persistent data structure.
Yeah, this is the point location problem. Okay. And as we saw way back in the beginning, right, this can be done in log, and I'm going to use a capital N time, in a data structure that uses n log of capital N space and construction time. Right? Now, why did I use a capital N here? Because the N that matters is not the number of sites, right? If we're thinking about this as a point location problem, then the important number is not the number of regions, but the complexity of the Voronoi diagram. How many different line segments are there? How many different vertices are there where line segments meet? Right? So we're going to have to answer, so we have 2 questions left to answer that we will tackle on Wednesday. The first is, what is the complexity of the Voronoi diagram? Okay? We know it has n regions, but how many line segments and vertices make it up? That's going to define the n that we need to plug into this point location data structure. Okay? And you're welcome to try and figure that out. It's a good exercise. The other really much more challenging question is, how do we build this Voronoi diagram so that we can feed it into the point location data structure, right? How do we identify all of these line segments that make up the Voronoi diagram? Right? We could do it the naive way, right? Take all of the perpendicular bisectors and figure out where they run into each other and stuff like that. That's going to turn out to be way too slow. So the focus on Wednesday will be on a really cool algorithm that builds the Voronoi diagram really quickly, which then lets you solve nearest neighbor by reduction to point location. All right? I'll see you Wednesday.